Good afternoon, everyone. Before starting our seminar, as we usually do, I wanted to introduce you by Univ, probably mispronounced. He's a postdoc, but will be here, will be with us at least for 1 year working on Condensation. His office is here downstairs, so welcome to this event.
Hello everybody. It's a pleasure to have with us Luiza Angheluta. She's an associate professor at the University of Oslo, the physics department, and she's also a co-leader of the Gross-Pitaevskii program on interface dynamics in geophysical flows at the University of Oslo. Although she is originally from Romania, she started her research career at the Niels Bohr Institute in Copenhagen. At the University of Copenhagen, doing the bachelor and the master under the supervision of Emergence, if I understood properly. Then she moved to Norway and she's the PhD in Norway, supervision of Joachim Mathiesen, on some project on interfaces in reactive and deformable interface flows. And after this, she moved to the States, to Chicago. Neil Goldenfeld, she was working also with him on problems of nonlinear convection and the formation of plastic deformation of crystals. And then she returned back to Norway, where she's working with several topics, but most of the topics of interest are dispersion, reactive transport, plastic deformation of crystals, interactions with topological defects, vortices, dislocations, interface dynamics, and quantum and classical turbulence. And a mixture of quantum and classical turbulence and topological effects is what will be the subject of today's talk. So, Luiza?
Thank you so much.
Next Nobel Prize. No, she has already, not the Nobel Prize, but she has already some the Fritz von Nansen Award, which is also a Norwegian award, but not for young research.
From the Academy of Science, yeah. Thank you, Emilia, for the nice introduction. Well, I'm following the path of my mentor, so I'm interested in many things. You can't really define me, per se, because I changed my interest from a couple of years. I'm not feeling at my best today, so sometimes I'm going to sit if I feel too uneasy. But I chose one of the topics today, the one that I'm mostly fascinated at the moment, and it's this analogy between classical turbulence and quantum turbulence. And in particular, the story that I want to tell you today about is the vortex clustering in two-dimensional turbulence. I don't know how many of you are familiar with turbulence, quantum turbulence, so I'll try to be accessible to a large audience. This is an overview of my sort of research theme. If I want to put it in a box, I needed to put it to apply for funding. So it's basically the multiscale dynamical Earth, and it has two branches and some interconnections between them, mostly at this level. I think there is a mathematical analogy between dislocations and vortices, and the question is, how will this propagate onto larger and larger scales? Most of people from earth science are interested in what they see at large scales. In geoscience is the patterns, the localized patterns, the shear zones, like the faults. And in atmospheric flow, you have the pattern formation on large scales, like the hurricane. And the questions that I'm trying to ask in this project is sort of like, how do we understand those patterns from the microstructures? And if you go very much deep, most of the rocks have a crystalline structure, and they have defects, and those defects have a topological feature, and they are called dislocations. And the same with hurricane. If you break it down to the very small scale, it has to do with turbulence, has to do with vortices. They're also topological. And in fact, they belong to the same topological class, so they are topological defects of codimension 2. They have a lot of similarities, also differences when it comes to dynamics. But obviously, there are some structures, because this is my personal take on it. Because these locations are intrinsically very dissipative structures, they will form lines because the interactions between them is along a line, whereas with vortices, they tend to be more conservative structures, not fully conservative, but they tend to rotate around each other, and then they form cyclones. But anyway, forget about this part. This is the topic of a different talk, and I'm going to focus a little bit on this. And then there is also the link between them, which is yet another things to explore. So the overview of this talk is to start off by telling you a little bit about two-dimensional turbulence and if it actually is something that we see in nature or is a mathematical beauty. And then I'm going to talk about the vortex clustering as the negative equilibria. This is the study that was originally initiated by Onsager approach to turbulence, to statistical turbulence. And then some of our numerical simulations with the Gross-Pitaevskii dynamics and with an augmented point vortex model, where we do study this vortex clustering as a non-equilibrium phenomena. And then the link between the vortex clustering and one of the essential features of turbulence, two-dimensional turbulence, which is the inverse energy cascade. All right, so two-dimensional turbulence is actually seen in nature. It's a good approximation for most of the atmospheric and oceanic flows because the depth usually is much smaller than the other dimensions. So it's quasi-two-dimensional. And in fact, you do see some of the fundamental features of two-dimensional turbulence, which is this large-scale coherent structures that are very long-lived, persistent structures. And you see them on the Earth atmosphere, and you see them on the Jupiter's atmosphere with the great red spot. But since the experimental realization of the Bose Einstein condensates, and in particularly the recent technique where they could squeeze the harmonic trap into one direction, so they have this highly-oblate sort of confinement, it is possible to access two-dimensional turbulence in superfluids. And this is a recent experimental realization from 3 years ago. And so the way the turbulence is excited in this superfluid is with like a laser beam that sort of it stirs the condensate. And then in the wake of that laser beam that you see this dark spot here, a lot of vortices are formed and then they interact. And there is some evidence that there is sort of like an inverse energy cascade, and there is some experimental evidence, particularly in this relaxation to decaying turbulence experiment, where you stir it, produce a lot of vortices, and then you remove the laser and let the vortices evolve. And they evolve into structures that look kind of like a coherent structure there. And in fact, with atmospheric turbulence, it might be quasi-two-dimensional, but there's other things that come in there. It's a much more complex problem. But in here, it's a much more accurate realization of two-dimensional turbulence. So this is the focus that. So I'm going to use quantum turbulence as a way to approach two-dimensional turbulence, as an experimental realization of two-dimensional turbulence. So I was mentioning about the inverse energy cascade, so I should probably talk about the direct energy cascade, which is the main feature of statistical turbulence, and it goes back decades ago to classical works of Kolmogorov and Richardson. Richardson was put it in a poetic way, that the transport of energy in 3 dimensions is via a breakdown of eddies. So you stir your fluid at a particular scale, usually at the large scale, at the container scale, and then you produce a large eddy, and that one breaks down into smaller eddies and smaller eddies until you reach the dissipative scale where everything is smoothed out by viscosity. Right? So you have this cascade into steps. And Kolmogorov was the one that formalized this picture and put forward the idea that if this happens, then the energy spectrum has a self-similar profile in the K-space with a universal kind of exponent -5/3. So this is the exponent that everybody talks in turbulence, especially statistical turbulence, the -5/3. And that's one of the features that I'm going to be presenting to you as well. And there's a relatively back of an envelope calculation to extract that exponent, and it's based on one essential ingredient, and that is that the injection rate is equal to the energy flux across scales, and it's equal to the dissipation rate, and that's epsilon. And then bidimensional analysis, then the velocity at the particular scale, L, will be proportional to, well, how do I use the laser? L times epsilon to a power of third, because the epsilon scales with like the energy per time, and you multiply with L, divide by that. So that means that in the K space, the velocity at the particular wave number will scale as the wave number to the minus a third. So if you convert that to an energy, that means that the energy spectrum will go to a minus 5/3. So that's an easy way to get it. Reality is that this dimensional analysis doesn't work in three-dimensional turbulence because you have intermittency, so all these exponents have corrections. The correction to this one is very small here, but if you go to higher moments, you see the anomalous scaling, which is the signature of three-dimensional turbulence. 2D is it's fundamentally different, actually, for the reason that we have two conserved quantities. Actually, in 3D, you also have helicity, and then there is a lot of work recently where they claim that you could produce an inverse energy cascade in 3 dimension if you tune the helicity conservation law in the correct way. In 2 dimension, we have the entropy flux, which is a measure of the rotation. So if the kinetic energy is a measure of the inertia, the kinetic velocity, the entropy is the square of the vorticity. I'll be introducing the vorticity later on. But because of that, then in the K space, we have a transport of 2 different quantities. And it's so that the energy will tend to go upwards or to larger scales, whereas the entropy is going to go down, right? And that produces 2 inertial ranges, we call. One, which is dominated by the energy flux, and that will carry on with the minus 5/3. And the other one, where it's dominated by the entropy flux, goes with minus thirds. And by a similar calculation, as I showed you before, but instead of using the energy dissipation rate, you use the entropy dissipation rate as your conserved quantity, you can find out this exponent minus 3. Okay? So this is what we call by an inverse energy cascade. That means that you are pumping energy at this particular scale, at an intermediate scale, and some of it is going to go up onto larger scale. Of course, this is a blow-up problem. So the energy has to be removed at the very large scale. So that's why in 2 dimension it's a very complex interplay between the role of the outer boundary condition as a way to suppress the energy buildup. So if you don't have any way to remove the energy out of the system, it's just going to build up into the very large scale. But fortunately, we have the drag with the wall that is going to take care of some of that. But the origin of an inverse energy cascade is still a little bit unclear. There's a couple of mechanisms that have been proposed in the literature. In the context of classical turbulence is the stretching of the vortices or the clustering of the vortices. For the quantum turbulence, where vorticity is quantized, as I will explain to you in a bit, it is the main mechanism that stands out is the clustering. So then we say that the origin of an inverse energy cascade in 2-dimensional turbulence is because of the clustering of the vortices into bigger and bigger ones. And there is the subtle difference between clustering and merging, whether the cores are going to merge and eventually it's like a big cluster with like double the circulation, or they just stay together and when you coarse grain the picture, it looks like a bigger one. And that's kind of the difference between classical and quantum turbulence. Okay, if you have any questions, stop me anytime. So let's go a little bit on the nature of the 2D turbulence and define the quantities that I'm going to use. So, so one important quantity in 2-dimensional turbulence is the vorticity field, which measures the circulation in a flow, and it's given by the curl of the velocity field. And by the nature of 2-dimensional velocity field, when you take the vorticity, it becomes a scalar. And that's a crucial difference, because then the equation from the Navier-Stokes, which I'm not, everybody starts turbulence from the Navier-Stokes equation. I'm starting from something else. But from the Navier, I'm assuming that you are kind of have you know or not the Navier-Stokes equation. But anyway, from the equation that describes the evolution of the velocity field, you can actually write the evolution of the vorticity field. And it looks something like this in 2 dimensions. And there's one important term that is missing, and that's the vortex stretching term. And it's the coupling between the velocity and the vorticity in a way that in 3 dimensions it produces the vorticity. And for some community, this is what they call turbulence. For mathematicians, most of the mathematicians work in turbulence, they would say that turbulence is the thing that happens when you create vorticity. So that means in 2 dimensions, you don't have any vorticity creation, hence it's vortex dynamics. Statistical physicists will have a different approach, and they will say that there is turbulence in 2 dimensions because you have an inverse energy, because we define turbulence in terms of this transport across scales, in terms of cascades, and you do have cascades in 2-dimensional turbulence. Yeah, but the velocity only has components in x and y. Because it only has in the z direction. Yeah, that's what I was talking about. It's 2-dimensional. So that's the feature of 2-dimensional turbulence. Okay, that's a good question. Yeah, very good. Now you can invert the equation of the first equation here, and you can also write down, if you know a vorticity field, you can calculate the velocity field by the Biot-Savart law. Right? So the feature of that is that then the velocity basically in a 2-dimensional flow that has circulation will decay as 1 over the radius, like this. And this property comes from the fact that if you calculate the circulation, so if you do the integral over a closed loop of the velocity field, then is a constant gamma. Now for classical turbulence, gamma can take any number. It's not conserved. For quantum turbulence, it is a quantized property. It depends on the Max Planck and the mass of the condensate, the condensate atoms. Okay, so now we can go into the limits. So there is the viscosity here of a normal fluid, which in a turbulent fluid, the viscosity is very small, however, is non-zero, and that's important. But one can take the mathematical limit of 0 viscosity and get into this, the Euler equation, or the dry fluid limit. And in this case, it is possible to decompose the vorticity field into a set of delta functions with a certain strength, like the circulation. So you imagine that you have point vortices. Each point vortex has a circulation that can be plus or minus, depending if it goes clockwise or anti-clockwise, right? And in this case, it's possible to show that the conservation law of the vorticity field maps into a set of ODEs for this point vortices. So this is the point vortex model. It's highly nonlinear with singularities and stuff like that, but it captures 2 main types of interactions. So you have a vortex pair. So if the point vortices have the same circulation, they're going to circle around each other, right? This is the Hamiltonian dynamics. And if they have an opposite sign, they're going to drift together. So a dipole drifts in a particular direction, and a pair co-rotates. All right, those are the 2 types of interactions. Of course, when you have many, you have the collective effect, and then it. Now, Onsager used this point vortex model to shed light on turbulence. Now you say, well, turbulence is completely different from the Euler's equation, right, with 0. So I agree with you, but in the lack of anything better, people have used statistical models of turbulence to infer about turbulence in the range that is far away from the dissipation range and the inertial range, because and the injection range, because you have this injection range, dissipation range, and in between you're pretty much like a conserved system. So that's quite crude, approximation, but still. So what Onsager did was to formulate a model and show the existence of these large-scale structures as equilibrium patterns that are seen in this Hamiltonian system. And so he started by noticing that, that the phase space in 2 dimensions for this particular system actually coincides with the real space. So it's an interesting statistical mechanics problem because it doesn't have any momentum space. Everything is in the coordinate space. And it's easier to see it when you write these equations here in terms of a Hamiltonian that looks like this. And of course, when you bound the system, which you have to do if you want to have a finite phase space and a finite box, then you need to take into account the images, the point vortex images. And the insight that he had was that because the system is bound, the phase space volume is going to be bound too. So when you coarse-grain and you define an entropy and an energy of the system, a thermodynamic entropy and an energy, then the entropy is going to be finite because the phase space volume is finite, right? Which means that if you plot the entropy as a function of energy, it's going to have a peak and then it's going to go down. That's very interesting. It's going to be a convex function, right? So now we know the thermodynamic temperature is defined in terms of the slope of this curve, right? And defines beta, which means that beta is going to be positive on this part of the curve, but it's going to be negative on this part, right? And later on, people have shown that this is indeed the case. There is this is kind of the shape of the entropy as a function of energy. And essentially, in a point vortex model, a conservative point vortex model, we have 2 phase transitions that are happening and are relatively recently studied in the quantum turbulence community. One of them is the Costa-Distaules transition, from basically the unbinding of dipoles at a particular temperature. And the other, but this is a positive temperature that is happening here. And the other one that was realized by Onsager is the Onsager vortex condensate that is happening at the temperature that is proportional, that it sort of depends on the number of particles in the system size. But you can calculate that transition quite accurately. So what happens at very low temperature is that all the particles are trying to find their nearest neighbor with opposite sign and pair together. And as you increase the energy, they become more and more dynamic. And at some point, they form like a well-mixed system. So when beta is 0 or infinite temperature, that's sort of the neutral homogeneous system. And then when you put even more energy, they're going to try to, even though they're trying to collapse together into 2 clumps of positives and the negatives. And this is the 2 coherent structures that emerge in a 2-dimensional turbulence system in a 2-dimensional turbulence in a finite domain, right? So how do you realize this? In classical turbulence, the Onsager condensates have been realized in decaying turbulence experiments. Yeah? And in quantum turbulence, the analog of the decaying turbulence is something like this. When you stir the condensate and then you remove the stirring and let the system evolve. And the way it evolves is through annihilation of dipoles. And they will emit some phonons. And eventually, the system will collapse into a state with 2 condensates, one in a certain rotation and the other one in the opposite rotation. So there's a recent paper that proposed that this mechanism actually is like an evaporative heating mechanism. So it's not the dissipation, the viscous dissipation as such, that allows the quantum turbulence to relax to the condensate. It's not the viscous dissipation, but it's a much more complicated dissipative term, which is termed by this evaporative heating, and it has to do with removing the coolest particles in the system, which is the dipole, will basically increase the energy per particle for everybody else. And if you increase the energy enough, then you get into that phase diagram regime where you have the condensate. So this is why it's like evaporative cooling, but it's the opposite. Removing the coldest heats everybody else.
So if you say that they don't understand why they cannot emerge. I understand that they can.
Well, they could, but the barrier is very high. So instead of doing that, the potential barrier, because the vortex will have a profile, and in order for the two cores to merge, it takes a lot of energy, and that realistically doesn't happen. So realistically is that they were going to try to cluster together and form patches of vorticity like that. Yeah, but whereas in the classical turbulence, where they have a very diffuse core, they can just merge together much easier. There's no penalty term. Right, but so I showed you that at equilibrium you can see these coherent structures, and you can approach them via a decaying turbulence, right? But most of the turbulence, like if you think about the atmospheric flow, it's not a decaying turbulence, it's always maintained, it's a driven system. So how do we see this condensates forming in a driven system where you do have an inverse energy cascade? Because in all these decaying turbulence experiments, there is no inverse energy cascade. What happens is the energy spectrum associated with the point vortices, which goes as k to the minus 1, and then the peak related to the condensate. And we want to find out what's happening in a driven scenario, when you have driven turbulence with the coexistence of the cascades and the clustering. What does the vortex clustering do in that case? And our conjecture is that the vortices were going to cluster, but they're going to form a self-similar distribution of coherent structure. So there's not just a particular sign, a particular cluster that are going to dominate the system or a particular size. They're going to have a self-similar size distribution. And that has to do with the statistical invariance sort of the vorticity, which is kind of something that is known in classical turbulence, but no one has discovered it yet in quantum turbulence, at least to my understanding. So we're bringing that analogy between classical and quantum turbulence a little bit farther. So this is the experiments done by my student. This is numerical simulation of the Gross-Pitaevskii equation. It's the damped Gross-Pitaevskii equation, and this is so psi is the many-body wave function of the condensate, and gamma is the damping coefficient that has to do with the finite temperature. And then, in addition, we have this the stirring potential that has two components. One is the trap, so we have this the harmonic trap, and the other one is the stirring potential that mimics the laser, that is sort of the laser beam that is our stick with which we drive the system. And the plot here is sort of a layer of different analysis. One was just the psi field plotted, and then it was a map from the psi field to the charge distribution where we can identify the vortices with the different signs. And then we threshold that field, and we locate the particles. So we have the positive sign and the negative sign vortices. And then later on, we do the cluster analysis to find the clusters, and then we can do the statistics of the clusters. So we have the stirring potential. Very good. So with this, we can calculate the energy spectrum associated with them, with this system. And we find that if you take into account all the if you calculate the energy spectrum with no analysis whatsoever, you get something as the blue curve, right? There's not much showing up there. There's the -3, but this actually is not related to the entropy cascade, but it's also a feature of quantum turbulence, because the shape of the wave function associated with the point vortex is so that in the k space has the k to the -3 spectrum. So this is really the spectrum of a it's not a point vortex anymore because it has a core. So it's the structure of the core. It's the structures of the vortex core that has the -3 scaling. And here there should be something emerging that goes with the k to the -5 thirds, which is sort of the signature of two-dimensional turbulence, if that would be the case. But it only shows up if we calculate the energy spectrum associated with the cluster vortices. So we take away all the guys that are not clusters and basically spoiling the system. And the reason for that it's not so prevailing is because the system is very small and it's very difficult to go to bigger system size. And that's one of the problems, I would say, with the experiments in the Bose Einstein condensates. They're very small, there's finite temperatures effects, and then everything is buried in these two major things, the finite size effects and the temperature effects. But we could show that if you do a proper analysis and really look at the clustered vortices that play a role for the inverse energy cascade, they do have a signature. And in fact, Novikov then was the one to really relate the spectrum or the distribution of the particles in a cluster with the energy spectrum. And he considered an isolated cluster. And he said, if that isolated cluster has a certain spatial distribution, then it will basically map into an k to the minus 5/3 energy spectrum. And it has to have a fractal. So if you have like a fractal cluster of point vortices, then you get the energy scaling. Of course, it's very idealistic because you have to have just one. That's not realistic at all. But the idea is that when you have a system of point vortices, you can actually calculate an exact relation between the distribution of point vortices and their induced energy spectrum. And it's a calculation that is pretty straightforward, and but it will be quite tedious to just go into the mathematics right now. But this is the formula that relates the spatial configuration of point vortices with their energy spectrum. Now, if you cos-grain it and you do an average, then you can relate the spatial configuration with the pair correlation function, right? And this is what it is, and it has the same property that in the limit of r going to infinity is going to go to 1, right? So the pair correlation function basically, the way it's defined here, it averages over the relative distance from a given particle to all the other particles, right? And what he postulated is that if this pair correlation function decays as r to the minus 4/3, then the energy spectrum per particle will have the k to the minus 1 contribution that dominates at large k, and the k to the minus 5/3, which just comes from doing this integration here. Magical, right? But why 4/3? There was no explanation for that. And then it's just one isolated cluster. And in reality, you have many clusters, and they interact with each other. So we were quite fascinated by this, and we wanted to understand a little bit better. So we did some analytics, and it's kind of hard to push the analytics too far when it comes to the energy spectrum, but you can go a little bit deeper when you look at the probability distribution of the velocity of a given vortex. Because every vortex induces a velocity on the other because they interact with each other, right? And in that case, we could calculate analytically this velocity distribution and find out how it scales with the system size and how it scales with the, well, because there was nothing special with minus 4/3 there, at least in Novikov's paper. So we said if the cluster will go to any power, alpha, then what will be the distribution of the velocity? So here, so you have to localize this cluster. So we say we have a vortex at the origin, and we have all the other guys around them. And we're asking what's the velocity induced by the presence of n vortices around? And depending on their distribution, what kind of velocity fluctuation will they have at the origin if you have a cluster? And through quite a tour de force, mathematically, we could find out that the velocity distribution will basically go with the power law. That depends on the spatial distribution exponent alpha, in this case for the velocity as alpha minus 2. So when alpha is 1/3, because we took in the measure of 2 pi r gr in 2 dimension, then we get that the velocity distribution will also go with minus 5/3. That's interesting, so the same exponent. But more importantly, it turns out that the density of the cluster is very much important for finding how clear the power law appears. And that kind of explained give us an explanation of the finite size effects that we would see in the Gross-Pitaevskii equation. Because if you could go to the limit of of a very dilute system, but still with enough particles, then you would have a pretty big scaling. But there's a critical density beyond which you cannot see anything. So if there are too many particles, you are hindering the power law. That's what we observed there. So there's a critical density for a power law to be sustained. So then we moved to a driven dissipative point vortex model to analyze a little bit better the origin of this scaling in the pair correlation function and how it relates to the energy spectrum. And the model that we proposed recently, it's currently in review in PRL, starts with the conservative version. It's written in a different way, but this is the Hamiltonian version. And so we needed to add a dissipation term. And it's something that mimics the dissipation that happens in the Gross-Pitaevskii equation, and it has to do with the dipole annihilation, but also with the phonon interaction because of the finite temperature effect. So we added this term here. This is the thermal friction effect. So it's basically shifting, rotating the Laplacian again to the gradient. This is the rotated gradient that becomes conservative dynamics. And then we rotate it back into a regular gradient, and this is the damping dynamic with the damping coefficient, right? And this is what you see in this model. But in addition, we needed to have rules for annihilation of the particles. So if the particles of opposite sign will come together within a distance less than something, then we will remove the dipole. And we also need to have a spawning rate that mimics the laser beam that was stirring the condensate. So we're spawning vortex dipoles randomly, in this case, not just behind the stick. And the vortex distance is set up, and it's larger than the annihilation distance, obviously. So in this model, we can actually propose also a parameter for how turbulent the system is. So the Reynolds number, which usually measures the inertial rate, the inertial forces versus the dissipative forces. In this case, we say that the inertial forces is basically the typical velocity of a vortex separated by the mean scale separation. So it goes like 1 over the mean scale separation times the system size times r. And the dissipative parameter, the main one, is gamma. So in this case, L, because it relates to the mean, sorry, what did I do? Up, sorry. Because the mean separation scales with the density, it also scales with the square root of the mean number of particles. So this is our measure of the Reynolds number, and this is one way to collapse all the data into something that will show us the mean trend as we increase the Reynolds number. So the vortex number is going to fluctuate, and it turns out that it actually goes pretty similar. It can be relatively well described by the mean field rate equation, where we say that the number of particles basically die out with the square of the number, because you need 2 particles to form a dipole and to annihilate, and they're going to also be spawned with the constant rate. And then the solution of that one is a tangent hyperbolic, and this is the curve that is plotted here. And of course, you see some deviation at low Reynolds number, and the reason for that is because you have the number of particles is relatively low when you have other effects that are coming into the plane. Yeah, but since they are symmetric, the equations are going to be the same. So you just yeah. So the system is neutral, and then it's basically the total number of particles twice the number of positives. It's the same. But this is why it should be n plus times n minus, right, in there. But since they are proportional to n, in the end, we can turn it out all in terms of n. Yeah, but there is no symmetry there to require 2 equations. Yeah, exactly. But because we start with like nothing, and they just spawn, and statistically they get into a neutral system. Because we always create in pair, and we always annihilate in pair, and we start from nothing. So it's yeah. Very well. So okay, so now I want to show you the thing that happens in classical turbulence in 2 dimension, where you have a self-similar statistics of the vorticity. And I haven't seen that in the quantum turbulence, and this is the part where we make the link. So the dimensional analysis argument for this is that if you have a velocity field of an eddy of a typical size r, then the velocity will scale as r to the third, where epsilon is the energy transport rate, which is constant, right? That's what I showed before. And that would mean that in the k space, the velocity will go with k to the minus a third. And so the energy spectrum, like before, it's going to go with k to the minus 5/3. So you have the energy spectrum in here. And on the other case, you can also calculate what will be the vorticity at a particular scale r. And so it's just taking the curl of this thing, which means that you divide by r. So the vorticity, the typical vorticity over a distance r, will also scale as r to the minus 2/3, which means that if you take the square of it, which would be like a measure of the correlation, will go as minus 4/3. So actually that minus 4/3 exponent is related to long-range correlations in the vorticity field. Now, this is what I mean by statistical invariance of the statistical self-similar statistics of the vorticity field, which is directly related to k to the minus 5/3. And without going into the details, this also relates to the conformal theory of two-dimensional turbulence. But it requires more work for us to make the analogy to the quantum turbulence, and we haven't done that, so I'm not going to go into that. But this is where the self-similar correlation of the vorticity really affects the energy spectrum. And this is what we want to see in two-dimensional quantum turbulence as well. So if we go back to our definition of the energy spectrum in terms of the spatial correlation of the particles, and we constrain the picture, now we have to take into account, before, that's the generalization when you have many particles of two signs. Before it was just one cluster, all of them with the same sign, and there was no charge coming up here. But if you put the charge in there and you co-screen the picture again, then we get this pair correlation, which is kind of weighted. We call it the weighted pair correlation, because when you calculate it from the microscopic particles, it has the charge. So it's like a charge density correlation function, but since the charge here is really related to the vorticity, then it's really a measure of the vorticity correlation, because that one will actually have the two delta functions, but you can map it to a one delta function when you remove the origin. So this weighted pair correlation function is a measure of the correlation function in the vorticity field. And this is what we show from the point vortex model simulations. This is the calculated pair correlation function for a different Reynolds number. And we showed that at low Reynolds number, there is no scaling, because there is usually a particular size that just emerges. But as you go to larger enough Reynolds number, then we see the minus 4/3 exponent there. So that's quite cool. And then we also showed that this one has a very clear signature of minus 5/3, much clearer than in the Gross-Pitaevskii equation, where there was, here we also have the finite size effect, but we don't have the effect of the phonons and all the other things that could, the temperature effects are not so dominant here. So we really see a very clear minus 5/3, and it's interesting that it also depends with the Reynolds number. So of course, if you're not in the right turbulent regime, you might not see it. But if you go high enough, then you do see it. And this is just a plot where we showed the scaling with the images included, because you have to calculate the images because of the finite size effect. Yeah, so something like that. So this is the story. So to conclude, the idea is that the idea that I want to put forward is that turbulence looks like an emergent phenomena, and there are strong similarities between quantum and classical turbulence. In particular, the two-dimensional turbulence is dominated by the interaction of vortices, and this interaction is so that they cluster into coherent structures that really feed on the inverse energy cascade. But in order to sustain an inverse energy cascade, the vortices have to cluster into patches of vorticity that have a self-similar statistics. So this is the story. Thank you so much.
Questions or comments?
Yeah.
Because I didn't understand that it's this gamma that you put in. So you are considering the Bose Einstein condensates with Gross-Pitaevskii and you are putting losses.
Yeah,
Is
that's the usual way.
necessary? What happens if you put it?
Well, yeah, it is necessary to have that one. Of course, you needed to have it relatively small because you want to simulate the experimental, realization, which is always like the finite temperature. It's very small, but it's still finite. So there's always interaction between the lowest energy level with the higher energy levels of the atoms, and that will introduce the gamma term.
So you can derive this from microscopic modeling?
Not directly, but yes, there are some ways to calculate how gamma depends on the temperature. There are some papers from not too long ago, from 2 or 3 years ago. Yeah, I believe so. Yeah. Because if you remove it, then you get into the conservative version that doesn't have the turbulent features. So you need to have the gamma there because it's the only way you can remove the energy, and the system has to be dissipative and driven at the same time. Yeah.
Which is the driving field?
I'm sorry?
The driven, which is the driving force here?
The driving force is actually this stirring potential, which is basically a Gaussian, has a Gaussian shape, and the center of the Gaussian is making a circle around here. So this is the Gaussian stirring potential, and then the center of it is just moving.
So you are moving that.
Yeah.
So that's time.
Yeah, so this is a time-dependent potential. So I didn't explicitly write it here. But it's an additional Gaussian trap with a moving center.
How many breakpoints do you use in this situation?
Oh, that's a question that Odin could ask, could answer very easily. It is a spectral method, though. I think he used spectral methods in here. Yeah.
More questions?
Yeah.
Why you always say plus and minus 1 and not highly-oblate integers?
Oh, that's a good question. You could put a higher orders. Yeah, it's just for simplicity. We kind of rescaled everything in pluses and minuses, but you could introduce like units into it. Oh, here, actually, it's not plus and minus. It's something. In this color map, we should have put the bar. It doesn't go to pluses and minuses. It goes to something positive and something negative, oppositely. But I can't remember exactly what's the actual charge for this. But you're right. It doesn't have to be.
Look at the phase. You do not see it in this plot.
No, not in the original plot, but in. So not in this page. This is just the density field. You don't see it in here. So now I'm using a technique that I worked it out a couple of years ago for a different model. But when you have a complex order parameter, you can do a transformation from a field to a particle. So this field has topological defects, and you can extract them and their charge. You can extract the position and their charge by doing a couple of transformations. It's Mazenko that did this a couple of years ago, and we basically implemented numerically. And it's a very accurate and very fast way to track. That's another way, is how do you extract those? And yeah, so I like the Mazenko one because it's very elegant, and it's just like, field particle, transformations, and it's easy to implement numerically, it's stable. I think he deserves much more credit for those papers, because there are some, he has a bunch of papers, but they're not highly cited, and it's just up there, and I find them like quite useful, yeah. So we used Mazenko transformation to get this, yeah. Yeah.
To find some vortices of charge 2 or 3?
No, they would have the same charge. All of them would have the same charge. But the number...
there's only one.
Yeah.
Because in other very similar models, if you put a vortex of charge larger than 2
Yeah.
or more,
Yeah.
it splits immediately.
I think so. I think so. They will not even form charges of 2. But that's a good point. We should actually look more careful at the sign there.
More questions?
Yeah.
I have myself one. In the in the classical two-dimensional turbulence, there has been a long history since the papers of Kreckman and
Yeah.
the experiments were never clear, and now they begin to have some quality to see some to be sure that there is something quantitative, some numbers that can extract from them.
Yeah.
What is the situation in the quantum case? It has been 50 years of experiments in two-dimensional classical turbulence to get something that can be reliable. Is easier in quantum?
You mean like in terms of the energy
For
spectrum?
example, the energy spectrum was, I don't know, is the state of quantum turbulence is a cleaner system perhaps, or is...
You know, before I got into this, they would say it's like, oh, you could do everything in Bose Einstein condensates, but actually, because of the finite size effects, this is the best that you can see. This is what we obtain, and it's very much like what everybody else has it. It's within like half a decade, and when you come from statistical physics, where you need like at least 3 decades to be confident on the scaling, it's taken with a big grain of salt. So, yeah. So this is the main thing that people focus when it comes to the parallelism between classical and quantum. But then the vorticity statistics is something else that hopefully people are able to measure it as well.
Any more questions? No? Thank you.
Thanks so much.
We will be here intermittently until Friday, so if you want to work with her, just agree on something.
Yeah.